Hey everyone, good? All right. My name is Fahad Vora and I'm a non-thesis master's student, which means I don't technically have to do research to graduate, but since I'm really stupid, I'm doing some research with Dr. Kunefer and in some research in vibrations with Dr. Ertuk. So I thought it'd be really interesting to share some of the stuff that we've been doing, and specifically what I'm going to talk about today will come very close to as simple as you can get of a real world application of noise control devices, or from what we've learned from class. So I'm not going to go very much into detail about the equations and stuff, just going to give you a general overview of what we've been doing in the lab. So noise in a fluid system, in industrial settings, housings, plumbing system is fairly common. And you can have fluid pumps that can generate harmonic broadband noise. But the thing I'm going to talk about specifically today are fast-acting valves. So how many of you have noticed that if you, let's say you're at your kitchen sink, and if you turn on or off your faucet really quickly, there's you notice a pressure spike, or like a sound or vibration in the faucet. So fast-acting actuators, fast opening closing actuators can actually lead to pressure spikes upstream and downstream of the valve. So in residential systems, you just have a mechanical knob, but in commercial industrial systems, you can have like solenoid valves, which can be really fast-acting. And those pressure spikes are commonly known as hammers, and they can be these hammers can exist in like common residential plumbing systems, hydraulic systems, etc. So this is what a water hammer event looks like. This was using a solenoid valve in the sink of a Love building basement. What we did was we installed a pressure sensor really close to the valve and let the valve open for 3 seconds and then closed it immediately. So you can see the valve closing over here, and the pressure spike profile is something like this. On the y-axis, you have pressure in psi, and 2 or 3 seconds of time passes during this event. So can you guys tell me of classical method of noise control, classical passive noise control method that we can employ or use to reduce such pressure spikes or control these pressure spikes? We've learned a bunch in class. We used a piezoelectric pressure transducer. In a side branch configuration to the PVC pipe that we were using. So can you guys tell me any kind of methods we could employ to reduce this pressure spike, bring that peak pressure down? A resonator sounds like a good first step, right? So yes, you can use classical passive noise control devices like Helmholtz resonator, which we learned in class. It's interesting because the resonant frequency of the Helmholtz resonator depends only on parameters such as the volume and the neck length and the opening area, and doesn't have to do anything with the shape. So you can modify the device as you want. But since we're looking at low frequency noise propagation, if you do the math, let's say for a 100 hertz frequency noise, and for a cavity area that's comparable to a standard Advil bottle, you would need a neck length of about 15.8 meters, which is impractical. If you look at 1000 hertz, you would still need 15 centimeters or so, which is still, which is okay, but in industrial or commercial systems, you may have space constraints, so you may not be able to install like huge devices in confined spaces. So we go back to the equations and we see that the peak pressure of the profile that I showed depends on basically the speed of sound, the local speed of sound, and the change in the flow rate. What we can do is we cannot do anything about the flow rate. It's going to flow in the pipe as it does, but we can control the speed of sound. And the way we do this, the speed of sound depends, the local wave speed depends on a parameter called effective bulk modulus, which is the inverse of compliance. So if we introduce a soft material locally, that can change the speed of propagation of the wave, and you can reduce the pressure spikes that way. So you can have classical noise control devices that are modified slightly, so you can have soft liners installed in, let's say, a muffler, a silencer, a Helmholtz resonator that introduces compliance in the system. So you reduce the speed of sound, and that's how you can bring that pressure, that peak pressure down. So this is the transmission loss curve for this modified silencer over here. So this is the transmission loss with the liner installed, and this one is without, and you can clearly see the difference. So with the liner, you dampen the system more, and without, it's not that much. Specifically, what we've been working on in the lab is coming up with these several versions of these devices. They're called water hammer arresters. These are installed in a side branch configuration of let's say a pipe. So if this is your fluid pipe, your PVC pipe, and the fluid is flowing in this direction, you install these in a side branch configuration like this. And you can have these devices can be of different kinds. This one over here is a gas spring device. So you basically have an O-ring that oscillates, and you have air filled in this chamber, and when you have a pressure spike, it basically absorbs the pressure spike and dampens the vibrations. What we've been working on is a compliance-based water hammer arrester. So what we do is make some polymers with certain properties that basically do the same thing as these gas spring piston-based arresters. So can you guys think of one way that just these devices that are just filled with some soft material, some polymer, are better than these devices with a gas spring? Why do you think this might be? What might be the pros and cons of each to this specific application? Yeah, so in the gas spring type, you have a lot of moving parts because the spring is moving. Then you have these O-rings that are in contact with the walls of the chamber always, and it basically dampens using friction, so there's dissipation and energy loss that way too. But using this, you can install it in a side branch configuration. Well, first of all, it doesn't have any moving parts, so that's one edge it has over these devices in a commercial setting. So if you wanted to sell this product, it has less moving parts, and hence it is the preferred alternative to the other kind. Another thing is you can install these polyurethane-based devices in an inline configuration such as this, which you cannot do with a gas spring one because it would obstruct the fluid flow. Right? So just to kind of wrap up, let me show you performance of these different kinds of devices. So on the y-axis is the peak pressure, and on the x-axis is time. So you can see without any liners and no water hammer arrestor, no noise control device, you have peak pressures going up to about like 55 psi. The compliance-based liners, you can see the peak pressures going up to about 28, which is still a pretty good reduction if you convert that into dB. And free piston-based are still a lot better. So you can see it's almost like 5 or 10 psi. So their performance in terms of the reduction of peak pressures, it was still observed to be much better than the compliance-based water hammer arresters. But it's a continuous improvement, and what we're trying to do is identify and make polymers of basically optimize the polymer so that they can perform as well as the gas spring kind of arresters. And that's it. Any questions?